Okay, quick sound check. Can everybody hear me?
Yep.
Okay, good. Anyway, let's get going. So good afternoon, or good evening, or good morning, whatever, good night, wherever you are. So today's lecture is going to be about page faults, and in particular, we're going to. The plan is to cover or implement, implement a number virtual memory features using page faults. And the features that we're going to be looking at are lazy allocation, which is the topic of the next lab. We're going to look at the demand copy and write fork, demand paging, and memory map files, or mmap. And in almost, in sort of a series operating system actually implements all these features. So if you look inside of Linux, you'll see all of these features actually are implemented. In x86, as it stands, none of them are implemented. And in fact, what a page fault does in x86, if a page fault happens in user phase, it basically kill the process. Nothing interesting. And so in this lecture, we're going to explore what interesting things you could do in the page fault handler to actually implement these features. So this lecture is a little bit less walking through code and understanding existing code, a little bit more design level in the sense we don't even have code to look at. Another thing that's important to mention is that lazy allocation is the topic of the next lab, and hopefully it will push out today. And copy and write fork is going to be a topic of one of the labs, and mmap is going to be another topic of one of the subsequent labs. So this is going to, this is one of the interesting parts of an operating system, and we're going to be spending quite a bit of time on it in the labs. Now, before diving in sort of into the details, it is probably helpful to take a little bit of a step back. And so you can think about virtual memory having two major benefits. One is isolation. So isolation in the sense that virtual memory allows the operating system to give every application its own address space. And so it's impossible for one application to muck, or by accident or maliciously to modify another application's address space. It also provides isolation between the user and kernel address spaces we talked about quite a bit, and as you've seen in the page table lab. But sort of another view or another benefit of virtual memory that I alluded to a couple of times earlier is that it provides a level of interaction. The processor or the instructions all use virtual addresses, but the kernel gets to sort of define the mapping from virtual addresses to physical addresses. And that allows all kinds of interesting features, like the ones that I'm going to be talking about in this lecture. Hold on a second. And so the kernel controls this particular mapping from virtual to physical address space. And most so far in x86, that mapping has to be quite boring. In fact, in the kernel, it's mostly direct mapping. And there are a couple sort of interesting things that we do, what the x86 kernel does, with this mapping. One, as we've seen, is the trampoline page. It allows the kernel to map one page into many address spaces. Another interesting case that we have seen is the guard page to protect the stack, both in the kernel and in the kernel space, both in user space and in kernel space. But if you sort of think about it, so far that mapping, has been relatively static. You set it up once, maybe per user, the kernel page table mapping we set up once in the beginning, and for processes once at fork, and there the kernel doesn't really do anything else with this mapping. And what page faults gives us is actually to make this mapping dynamic. So I'm using page faults we can change, or the kernel can change the mapping. So dynamically on the fly. And this turns out to be an extremely powerful mechanism. So if you can combine page tables and page faults, you have an enormous, the kernel has an enormous amount of flexibility. And the flexibility really comes down because you can sort of change this level of direction on the fly. And so what we're going to be doing is basically looking at all kinds of usages of this dynamic remapping or dynamic changing of the page tables that gives us interesting features. So the first thing we may want to think about is a little bit is what information is needed. So if you're in a page fault happens, and the kernel wants to respond to this page fault. What information does it need to actually be able to respond? And it's sort of quite obviously we'd like to have the virtual address of the virtual address of defaulting or the cost of page fault. Let me not say it. Actually, what I want to say is the defaulting virtual address. And you've seen presumably some of these panic calls in your page fault lab, and the kernel actually has access to them. In fact, it prints them out when actually a page fault happens, and it happens to be sitting in the ST val register. So when a user application causes a page fault, the page fault basically invokes the same trap machinery that Robert discussed in the last lecture. It's almost completely identical, but in the case of a page fault, it also will put the defaulting address into that ST val register. So that is one thing that we probably want to know. The second thing that we probably want to know is the type of default. Because that may be in terms of, we may want to respond differently in terms of to a page fault due to a load instruction, or a page fault due to a store instruction, or a page fault due to like a jump instruction. So in fact, if you look in the RISC-V documentation, here's the RISC-V documentation, and here in the SCOS register that was mentioned in the trap lecture, there are a number of causes that actually are related to page faults. So for example, if you look at number 13 is a load page fault, number 15 is a store page fault, and then number 12 is an instruction page fault. And so these are the, in the SCOS register, and we get that information. And so there's 3 different types, the read, write, and instruction. And just going back, the one SCOS that actually was caused by the ecal instruction to do actually a kernel transfer is number 8. Right? So that's the one that we saw in the trap lecture that we spent a lot of time thinking about in the trap lecture. But basically, all the other page faults or exceptions use the same mechanism to transfer from user space to kernel to kernel space, and once in kernel space, in the case of the page fault, the ST val register set, the SCOS register set. Then the third thing that we probably want to know is the instruction, or the address, the virtual address of the instruction that caused the page fault. And anybody remember where, from the trap lecture, where that instruction is, or where that address is? Anybody?
Is it SEPC?
Yeah, exactly. And there was this register SEPC, correct? The supervised exception program counter. There is where it is, and where is that saved? As part of the trap handling code.
In the trap frame?
Yeah, it ends up in the trap frame, correct? There's a trap frame EPC actually has the exception program counter. So if you sort of think about the hardware mechanism and what x86 does, we have three pieces of information that are probably extremely valuable to us when we get actually page fault, namely the address of cost default, the type of default, and the exception program counter, like where did it happen in user space. And the reason that we care a lot about the exception program counter, correct, is because we probably want to repair, in the handler, we're going to repair the page table, and then we're going to basically restart the same instruction. And hopefully after repairing the page fault or repairing the page tables, that instruction can just run without any trouble. And so it's important that we can be able to resume the instruction that actually that caused the fault. Does that all make sense? Okay. So now I want to look at also the basic mechanism and the basic information that the RISC-V is actually giving us. And I want to look at basically go through a list of features that will help us understand actually how we can use the page fault handler to repair the page table and do interesting things. And so the first thing I want to look at is allocation, and in particular, S-break. So S-break is the system call that x86 provides that allows an application to basically grow its heap. Right? So when the application starts, S-break points here, at the bottom of the heap, at the top of the stack. And in fact, it's the same place where p size basically points to. And so when S-break is called, for example, S-break is called with like 1, 2, 3, 4, 5, the number of pages that you want to allocate. The S-break system call basically bumps up this boundary to something bigger. And so what that means that when the S-break actually happens, or the S-break system call is called, the kernel will allocate some physical memory, map it into the address space of the user application, zero the memory, and then basically return it from the system call. And every time, and the application can grow, that physical memory or memory that it needs or it might want by just calling multiple times to S-break. The application can also decrease or shrink its address space by calling S-break with a negative number. But I want to focus on the case where we're growing the address space. And in x86 as it is, the S-break is eager, or thus what I'm going to call eager allocation. Namely, as soon as the S-break is called, the kernel will immediately allocate the physical memory that the application is asking for. And now it turns out that in practice, it's actually hard for applications to predict how much memory they need. So typically applications tend to over-ask. And so they ask a lot more than they really need. Often that which means that basically, the address space will grow quite a bit, even with memory that's actually never used by the application. You might think like, oh, well, that's stupid. How could that happen? Well, think about like if you write an application program and a typical application program, maybe it reads some input or it has a matrix that it uses for some computation. And often the application writer sort of plans for the worst case. It allocates memory for the biggest matrix that the application might never ever need. But in the common case, the application may be compute with a much smaller, input or a much smaller matrix. And so it's quite common, in fact, for application programmers, and probably if you think about your own application you've written, to actually over ask and actually underuse. And we'd like to, in principle, not a big problem, but using actually virtual memory and page fault handlers, we can actually totally respond to that in sort of an intelligent manner, and by basically doing lazy allocation. And then the basic idea is very simple. At S-break, we're basically going to do almost nothing. The only thing that we need to remember is, of course, that we did grow the address space. So the only thing really what we're going to be doing is actually bumping up, piece size. Whatever with the number, set piece size to whatever the new size plus, n, and where n is the amount of memory that's allocated. And then, but we don't allocate, the kernel doesn't allocate any physical memory at that particular point in time. It doesn't zero it, it does absolutely nothing. Then at some point, the application will use or might use that memory, correct? If it's actually one of the pieces of memory that it really needs. And that will cause a page fault, right? Because we didn't map that memory actually into the page map yet. And so if we dereference a virtual address, above, this piece size, but below piece size plus n, what we like to be happening is that, the kernel will allocate a page and restarts the instruction. So if we get a page fault and we see that the virtual address is, bigger than piece size, is below, is below piece size, so piece size, then we know that this must be a virtual address, and I guess above the stack. We know that this is an address that actually comes out of the heap, but for which the kernel hasn't allocated any physical memory yet. And so the response to this page fault could be reasonably straightforward. In the page fault handler itself, we can allocate a page using kalloc, allocate one page, zero the page, map the page into the page table, so updating the page tables, and then basically restart the instruction. So for example, if it was a load instruction or a store instruction that wrote or was trying to read, from that not allocated, piece of physical memory that actually the process has, now after we mapped in this, physical page, the restart instruction should just work. Amir, go ahead.
Right. So I was wondering, in the case where we're doing eager allocation, and there comes a point where a process consumes so much memory that it actually exhausts the physical memory resource. Mm-hmm. If we don't do eager allocation, and we do lazy instead, at what point would the application know that there's no physical memory?
That's a great question. Well, basically, it almost looks through the application that there's this illusion of unlimited physical amount of memory. At some point, of course, it might use so much, that basically, okay, so it may use all the physical memory, and so if then it touches one more page for which there's no physical memory present at that particular point in time, then there's a couple actions that the kernel can take, and I'll talk about the more sophisticated ones later. What you're going to be doing in the lazy lab is, if the memory's up and there's no more free memory, you just return an error, or actually you kill the process in that particular case. And so because you're out of memory, so there's nothing the kernel can do, and at that point, you return or kill the process. That's what you're going to do in the lazy lab. We'll see later in this lecture, you could be more sophisticated than that. And I think this is generally brings up a topic that is, if we have a collection of processes running on an operating system, there's a limited amount of physical memory. And that limited amount of physical memory must be shared in some way between the applications. And so I'll talk a little bit much more about it in 10, 20 minutes. Okay, there's a question in the chat. why is the condition virtual addresses don't necessarily start at 0? Okay, because there's a question about this particular check here. Remember, we have our stack here, and we have our data here, and we have our text from the user process, and basically we bumped up, p size to something bigger. We bumped it up, the growth, but we haven't allocated memory here yet. So this memory has not been physically allocated yet. So this checks if the address falls below p size, and it actually is a valid, address in the user address space. If it were above p size, presumably that's a programming error, and the program or the user application is trying to dereference a memory that actually doesn't have. Hopefully that answers the question.
Yeah, thank you.
Okay, good. So to get a little bit of a feel, for what it actually means in this lazy allocation, and that's probably the only sort of programming or code things that we're going to be doing today is let's try to sort of sketch out or look actually how it would look in code. And the tool, you'll see that it will be surprisingly easy, and furthermore, it's probably a big help for the lazy lab. And so hopefully that will help you get going pretty straightforwardly. And it allows us also to look at a couple page faults.
I had a question actually regarding a point that I made in chat. Why do we actually need to kill the application? Couldn't the operating system just return like an error that said you are out of memory, try and do something else?
Let's postpone that question to a little bit later. And in the page fault, we're going to just kill the process. But we could be more sophisticated in the page fault lab. Real kernels are more sophisticated. Okay. Although in the end, they might still kill it. If there's just no more memory whatsoever to be gotten, there's basically no choice. So the first thing we're going to do, we're going to modify. So you remember that sysproc is, actually grows the address space of the application, allocates memory, and all that kind of stuff. We're just not going to do that. We're just going to set p size, to p size plus n. So let's assume that we're only growing and not worry about shrinking for now. And that is what we're going to be doing. So this grows the virtual address space by n, and that's all we're going to be doing. Let's see if I can make no programming mistakes. I did make a programming mistake. I guess I don't have proc p here, so I'll make proc. Good. So the program just runs, or at least reboot. I think if we do like echo hi, we're going to get actually a page fault. And the reason that we get a page fault is because the shell, who's going to fork, echo, and then the child's going to exec echo. The shell actually allocates some memory, and so the shell calls sbreak, and things are not looking good. But it's sort of interesting to look at the information here. So here's it prints out the scos register, or the value in scos, and we see it's 15. Anybody remember what 15 is? From that table that I just showed you a little bit a while ago, that actually is the write or store page fault. We see that it's process free. That's probably the shell. And we actually see the exception program counter. It's 1284. And we see the address, the virtual address on which we fault, which is 4008. And so let's look at the, we can look at the assembly of the shell. The make file is nice enough for us to actually generate that. And we can look at the address 12A4. And, we see indeed, there's a store instruction, right? The store instruction, and it looks like, that's where we're faulting. So if we scroll back a little bit and look at this assembly here, we see that actually this is in part of the implementation of malloc. So that seems totally reasonable, correct? Here's the malloc implementation. Not surprising that we presumably used sbreak to get some memory for implementing the user malloc, and we're basically initializing a free list of the using the memory that we just gotten from the kernel. And this line 12A4 presumably writes, I guess it writes something in size, and but we're writing to memory that actually hasn't been allocated. Another reason that we can see that the memory is probably not allocated is I think the shell actually has 4 pages of text and data, and we're basically sitting just above the 4th page and the 5th page. In fact, we're sitting 8 bytes above it. That sort of makes sense. We look at the instruction again. Where's 12A4? We see here that basically probably A0 holds 4,000, and 8 is the additional offset that we're actually dereferencing. So that's the default. And now what we like to do is do something slightly more sophisticated than we're currently doing. And so let's go to proc trap.c. And look at user trap, right? Because this happens in user trap. User trap is the function that that Robert discussed a week ago, and it just goes through the different causes and performs some action. So we're a little bit here. This line is s causes 8, and that's the point where we're going to do process system calls. Then there's a line that checks whether there was any device interrupt and processes inside of the device interrupt. And if there's none of those two happen, then basically we get this trap, and the process is being killed. And basically what we need to do is, we need to add some code here that, checks for another case, right? Basically, I guess the case that we want to look at is if our s cause our s cause is 15, we want to do something else. Does that make sense? So what do we want to do here? What is sort of the plan for attack, for these couple lines of code? Anybody?
We want to check if P size is more than the virtual address, not in stval, perhaps.
Yeah, go ahead.
Oh, and this is the case, then do something like UV malloc, I think.
That's one way we could do it. So I'm going to cut some corners just as a demo, and presumably in the lab itself, you will need to do a little bit more work. But basically, here's the sort of, I think, the frequent second of code that we need. So let's see where I was. Here's user trap. And let me just kind of paste it into it, and then we can look at it. Just a print statement for debugging. And basically, what I'm going to do in this handler, I'm going to allocate a physical page. If there's no physical page, meaning we're out of memory, we're going to kill the process for now. If there is a physical page, we'll zero the page. And then we just map the page at the appropriate address in the address space of the user. And in particular, we map it on the rounded down virtual address, right? So the faulting address is 4008 here. And so that's 8 bytes into the 5th page. And we want to map that physical page at the bottom of the the virtual page, so at 4000. So round it down to 4000, and then we map 4000 to this physical page. And then, of course, we have to set the usual permission bits, the U bit, the read and write. Does that make sense? And I guess I can get rid of this line. So let's try it out. And I guess I made some mistakes.
I think that on the else, you don't have an opening bracket at the bottom.
Oh, yeah. Else if, no, I do have it. Do I need one more? Oh, yeah.
Oh, sorry, I meant on the else right here, you don't have an opening bracket, right? Like, when it says else printf user trap unexpected cause.
Yep, thank you. That hopefully will help a lot. Good, excellent. So echo hi. Now, of course, we're going to be optimistic and we hope that works. I'll tell you it won't work, but we did get 2 page faults, right? We got a page fault at 4008. Apparently we processed them because we got another page fault. And so now the only problem that we've left is there's a UVMF, complaining that there are some page that we're trying to unmap is actually not mapped. And what could that be? Why would you think even we get this panic? Anybody? What memory is being unmapped here? Most likely.
The one that was lazily allocated and not actually allocated.
Yeah, exactly. The memory that was lazily allocated, but actually hasn't been used yet, right? And so there is no physical page for that particular lazily memory. And so this case, when the PT is 0, there's no mapping yet. That's not really a panic. This is actually what we expected, could happen, right? And in fact, for that page, we just don't have to do anything, right? We can just continue, go to the next page. Does that make sense? So let's do that. And now let's do the echo high, and boom, we got 2 page faults, but high works. And so we're basically, have sort of a very basic, minimal lazy allocation scheme working. Any questions about this?
Sorry, I didn't really follow why you could just continue. Could you explain that again?
Yeah, so the bug indicated, correct, that we're trying to free a page that actually is not mapped. And how could that happen? Well, the only reason that could happen is because S-break moved up piece size, but the application never used that memory. And so it actually has no mapping yet because it was actually not allocated, right? Yeah. Because we're lazily allocating, we're only allocating physical memory for those pages when we need it. If we didn't need it, then there will be no mapping. And so it's totally reasonable that there actually is going to be a case where there's no mapping for a virtual address because it actually wasn't allocated yet. And for that case, we just have to do nothing. We can't free the page, correct? But there is no free page. And so the best thing is to do continue and just go to the next page in the loop.
Okay, that makes sense. Thank you.
Yeah, if we didn't do continue, but basically, just kept going, then we would actually free the page. And that'd be, we can't do it because there's no page. That's why the continue is there.
Makes sense.
Another question.
Yeah.
In UVM on map, I assume the panic was there for a reason. So
Yes.
would a more reasonable implementation is to have 2 versions, and we would use the one that doesn't panic?
Yeah, because why was the UVM the panic there? Well, there was basically an invariant that used to be true for the unmodified x86, right? Unmodified x86 should never have a case where there's user memory that was not mapped. And so therefore the panic goes off. We now changed the design of x86, and so we have to just, and this invariant is just no longer true. And so we got to remove the panic, and because that invariant is just not true. Or legitimately not true anymore.
I see. Thanks.
Does that make sense? So, so a couple of comments. This will hopefully help a lot with the next lab. And in fact, this is like one of the free components of the labs, of the next lab. So this is one of the first things you have to do. And hopefully this will save you some time, maybe make up for all the pain that you went through in the page fault lab. But clearly it's not enough, right? So like what things are, we made these changes, but what things are still probably broken? Now, one already was mentioned. I actually didn't do the check whether actually the virtual address was below piece size, correct? Which we probably should do. Any other things that might be broken? Anybody?
The number of bytes to grow the process by in S-break is an int and not an unsigned int, so negative numbers could be used.
Yes, and then negative numbers can use, and that means shrinking the address space, right? And so if we shrink the address space, we also have to be a little bit careful. So it turns out there's a whole bunch of, as usual, in an operating system, there are a whole bunch of different cases, correct, in which we're going to be looking at this particular page table entry. And for all those different cases, we might actually have to modify x86 slightly. And that's exactly what basically the lab is about, is doing good enough job that basically you can pass user tests. And user tests will stress a whole bunch of other cases that you will need to deal with. Okay. Any questions so far? Okay, let me, in that case, I want to talk about a bunch of other usages or cool things you can do once you have page faults and page tables and you update them dynamically. Another one that is almost trivial, but commonly used, is what's called zero fill on demand. It turns out that in operating systems, there are many null pages. So, for example, if you look at an address space and user space, x86 is not advanced, but like if you look at the layout of a binary, an A.out, there's some text, there's what's called the data segment, and there's typically also something that's called the BSS segment. And so when the compiler produces the binary, it basically fills in these three segments. The text is the instructions. The data is basically global variables that actually have a value that is not zero. So an initialized data. And BSS is basically a description that says, well, there's a whole bunch of variables, and it lists basically their sizes, and they all should be zero. And the reason that they're basically not listed out, or the memory is not right there in the file is because, that'll save a lot of, for example, if you declare a big matrix in C on the top of a file as a global variable, and it's automatically should be all zeros. Why allocate all that space in the file? Just like note that basically, for this particular variable, the content should be zero. And then basically on exec, on a normal operating system, on exec, we'll look at these three segments, and thus the usual thing that x86 does, for text and data. But then from BSS, it will allocate, memory to hold the BSS and basically stick zeros in there. So, it will allocate an address space, sticks the data in it, sticks the and then basically, the equivalent of the BSS, all the global variables that basically are zero, and that may be many, many pages. And all those pages basically have to have the content zero. So that's the virtual address space. And so a typical trick, to do is to say like, wow, I got so many pages that need to have zero. What I'm going to do in physical memory, this is the virtual address space, and this is the physical address, memory. What I'm going to really do is I'm just going to allocate one zero page and fill it with zeros, and basically map all the other pages to that one page. Saving myself, lots of physical memory, at least at startup. And of course, those mappings have to be a little bit done with care. We can't mark it, we cannot allow writes to it, right? Because everybody's relying on the fact that it actually stays zero. So we just map it read-only. And then at some point, when an application starts writing to one of basically does a load or a store to one of the pages that actually are part of the BSS, so because it wants to whatever, store a 1 or 2 or variable content in there, we're going to get a page fault. And so what should we do on the page fault in this particular case? Anybody? Anybody idea what should we do in the page fault here?
I think we should make a new page and write zeros there and rerun the instruction.
Yeah, exactly. So let's assume just for my drawing that actually the store instruction happened to the one at the top. And what we really want to do basically is allocate a new physical page, a new page in memory, calloc, put zeros in there because that's what we're expecting, and then we can change the top mapping, right, for the one for this particular, I guess for this guy, or actually, let me assume that it's this one. We can change this mapping, to be read write, and point it to the new page. And then, basically, so copy plus update PT, and then restart instruction. And that's it. And why is this an effective, why do we think this is actually a good optimization? Or why do operating systems do it? Anybody?
You don't need it.
Yeah, go ahead.
You don't need to use as much memory as the user requests, so it's just better to fill it when you need it.
Yeah, actually, it's similar like to the lazy allocation. Basically, if the program, say, allocated a huge array, for the worst possible input, it's a global array. It all has to be zeros, but maybe only a fraction is being used. Right? What's the second advantage? Second advantage is you have to do less work in exec, right? And so the program may start quicker and get basically better interactive performance, because you don't really have to allocate memory. You don't really have to zero memory. You only have to allocate the 0 1 page, and the rest is you're just mapping the page tables. You just have to write the PT entries. Does that make sense?
But aren't updates or writes so they will become slower because every time a page fault will occur? And
yeah, so that's absolutely a good point. So we basically postpone some of the cost to later, right? At the point that we do the page fault, and we're partially relying or hoping that maybe not all the pages are being used. But like, for example, if the page is 4,096 bytes, basically we're going to take one page fault per 4,096 zeros, right? And so there's some amortization there. But it's a great point. Certainly we have made we have added the cost of the page fault. How much is the cost of the page fault? How should we think about that? Is that comparable to a store instruction, or is it much more expensive?
More expensive, right?
Yeah, why?
Well, a store will just need to require, it will take some time to get through to RAM, but the fault will have to go to the kernel.
Yeah. So in fact, how many store instructions were there even in the trap handling code that Robert showed you last week, or actually that you're doing currently in the trap lab?
Well, at least like 100.
Yeah, at least 100, right? Just to save and restore registers. So there's quite a bit. And so there's both the overhead of transferring from user space to kernel space, as well as all the instructions that are being executed to save and restore state. So the page fault is definitely not free. So the question that was asked earlier is a very good question. Okay. So let's look at some more optimizations. That one can do. These ones are sort of reasonable boring, or maybe reasonable straightforward. And we're going to hopefully get a little bit more, a couple more exciting ones. Let's see what is the next one I wanted to do. The next one is a very common one. And many operating systems implement it. And in fact, it will also be one of the topics in one of the labs. So let's do the next one. And that is copy on write fork. or sometimes called cow fork. And the observation is pretty straightforward. In fact, we made this observation a couple times in lecture. But when let's say the shell, right, that in fact we saw it a second ago. So like if the shell runs and it processes a command, it actually does a fork to create a child. And so the fork basically creates a copy of the shell. And so we got a parent and we got a child. And then the child, almost one of the first things it does is an exec. Maybe execute a couple of instructions, and then it actually execs, for example, to run echo. And as we now know, and we certainly saw it in the last lab, the fork creates a complete duplicate of the shell address space, and then exec, the first thing it basically does, it throws that away and then replaces it with an address space, containing echo. And so it seems slightly wasteful, right? Like, so here, let's say we have our parent virtual address space, and then here we have the child. And what we're actually doing, and here's physical memory. And in the normal case in XV6 or in unmodified XV6, there's a bunch of there were 4 pages we saw that the shell has, 1, 2, 3, 4. And when we when a fork runs, it basically creates a duplicate of those 4 pages, 1, 2, 3, 4, and copies all the content, from those pages, the parent into the child. And then as soon as the exec happens, basically we're going to free these pages and allocate new pages that actually have the content of echo in it. So a good optimization, one that actually tends to be very effective for this particular sequence, is that if the parent has these 4 mappings, in its address space, going from whatever, the 0 goes here, the first one goes there, and whatever. Instead, when we create the child address space, instead of copying and allocating new physical memory, what we could do is just share the physical pages that the parent actually already has allocated. And so we can just set the PTEs for the child, to the same, pointing to the same physical pages as in the parent. And we're going to be a little bit careful again, correct? Because if the child wants to modify one of these pages, that update should not be visible to the parent, because we want strong isolation between the parent and the child. So we need to be a little bit more careful. And so to be a little bit more careful, what we can do is just map those pages, both in the child and in the parent, read-only. And then, of course, we're going to get a page fault at some point, because the parent is going to run or the child is going to run. And maybe, the child or the parent will do a store instruction to maybe save the data to some global variable somewhere. And at that point, that will cause a page fault, because, we're writing to a page that is mapped read-only, so we get a page fault. And so what do we need to do? Well, we need to make a copy of the page. And so let's assume that it's the child that actually does the store instruction. So we allocate a new page. We copy, the content of the page that we're faulted on into this new page. We map that page into the child, and this time we can map it read-write, because it's now a private page only, visible in the child's address space. And in fact, the page that we actually faulted on, we can also now map read-write into the parent. And so we copy the page, map it, and restart the instruction. And when you restart the instruction really means, doing user read, the same way that we returned to user space in last week's lecture. Does this make sense? Any questions about this plan?
I'm sorry, when you say we map the parents' virtual address to be also read-write, how do we find it out? Is it the same as the child's? Or?
Yeah, because the address space of the child is a duplicate of the parent's address space, right? So if we fault a particular virtual address, since the address spaces are equal, it's the same virtual address both in the parent's address space and in the child's address space.
Makes sense. Thank you.
Another question.
Yeah.
For, let's say, like some parentless process, maybe like the first one that launches, does it use its pages, does it set just read permissions, or does it start off with read write? And when it forks, it modifies?
Okay, it's up to you. In fact, this is also one lab. You're going to implement copy and write after the lazy lab. And you have some freedom. The easy thing to do is just also map it read only. You will get a page fault, and then you'll do whatever you normally also would do in the copy and write. So you can use the same mechanism in both cases. There's no reason to actually specialize or do something separate for the first process.
Okay, thanks.
So I also have a question. Given that we like kind of copy whole whole pages around pretty often, does any like memory hardware implement like a specific instruction? Because basically memory hardware will usually just have like some data lines to say read me or store this memory. But we have like, oh, copy page A to page B.
Yeah, there's x86, for example, has hardware instructions for copying ranges of memory. RISC-V doesn't. But of course, in a very high performance implementation, all these reads and writes will be pipelined and hopefully run at the speed of the memory bandwidth. Note that actually, in principle, we might be lucky and we're saving, correct, on loads and stores or copies. Because in this particular picture, I made only one copy. And in the unmodified case, we would have copied all 4 pages. And so hopefully, this is just like strictly better, both in terms of memory consumption and in terms of performance. Fork will just be faster.
I have a quick question.
Yeah.
When the page fault occurs and we see that like it was essentially like we were trying to write to a read-only address, how does the kernel tell like that this is a situation where it's copy on write fork versus just a situation where the memory it was trying to write was marked as read-only for some like legitimate reason other than copy on write fork? Is it just kind of an invariant that if it's user memory, then it will be mapped read write unless it was a result of copy on fork?
Yeah.
Copy on write?
Yeah, so it is an invariant that needs to be maintained in the kernel, and the kernel must recognize in some way that this is a copy and write page, if you will. And so I'm very glad you asked the question, because turns out, the RISC-V hardware, almost all page table hardware actually has support for this. And we didn't mention it earlier, but here's our, our usual, whatever, 2-level or multi-level page table. Here's our PTE. And if you look in the PTE, I talked about the bits, 0 through 7, but not about these 2 bits, RSW. And they are reserved for supervisor software. So the supervisor software, this is the kernel, can use these bits at its own free will. And so one thing one could do is, like, say, decide that bit 8 basically means this is a copy and write page or a copy and write fault. And so when the kernel programs, these page tables for copy and write, it can just put on the PTEs, for these particular pages, the bit, set the bit copy and write, so that when the page fault happens and we see that the copy and write bit is set, then we just go off and do this. And otherwise we do something else. For example, maybe it's a lazy allocation. Does that make sense?
Yep, thank you.
And in fact, in the lab, one of the things you will be doing is probably use that bit, set a copy and write bit in the PTE. There's one more wrinkle that will show up in the copy and write lab, is that there's some, currently in x86, basically a physical page more or less only belongs to one process, with the exception of the trampoline page. which the sampling page were never free, so that is not really a particular big issue. But for these pages, now we have multiple processes or multiple address spaces pointing to the same physical address. And so, for example, if the parent exits right away, we got to a little bit be careful, correct? Because can we free that page immediately if the parent exits?
Maybe not, because there may be multiple children processes.
Yeah, there might be a child, correct, using that page. And so if the kernel would free that page, then we're going to be in trouble because basically if you look at K-free actually writes all kinds of ones on a free page. And so then the child runs with that page, all kinds of bizarre things are going to happen. So what should the rule be now for freeing?
Free if you don't have children, I guess.
Yeah, again, maybe a better way or sort of a more general version of that statement is to say, well, what we really need to do is we need to ref count every physical page. And when we free a page, we decrease the ref count by 1. And if the ref count reaches 0, then actually we can free the page. And so you will have to introduce some additional data structure or some meta information in the copy and write lab to actually do that ref counting.
Where can we store this? Because if we have to ref count every single page, that could be a lot.
Yeah, for every physical page of memory, you'll have to do a ref count. Yeah, you can get away with a little bit less, but we're for simplicity in the lab, we're going to just for every one physical, so for every 4,096 bytes, we need to maintain a reference count.
Couldn't we write that down in those other 2 free bits and say that no more than 4?
We could. Not unreasonable, but if you forward multiple times, that'd be too bad, right? And after 3 times or 4 times, you can't do the optimization anymore. But yeah, there's some freedom here.
Also, do you really need to use that bit to specify if it's a copy on write? Because the kernel could also maintain some information about the processes that share.
Yeah, you could. You could maintain some other meta information along with the process address space to say basically, well, virtual addresses between this and that are text addresses. So we have a page fault there, and it must be copy and write or something. And in fact, one of the later labs, you will certainly extend the meta information that x86 maintains exactly for that reason. There's a bit of freedom here when you start implementing these labs. Any further questions about this? Okay, then let's go to the next one. This is something that's called demand paging. Another very popular one in most operating systems implemented. And so this goes back basically to exec. So currently in unmodified x86, x86 actually loads the text segment and the data segment from file and maps it in eagerly basically into the page table. And basically the same observation that we made for lazy and zero filled is that, well, what we could do is like, why do it eagerly? Right? Why not just wait a little while until to see if actually the application really needs, those particular set of instructions. The binary might be very big, and instead of actually loading it all in, from disk, which tends to be expensive operation, maybe the data segment is much bigger than the typical use case requires. We don't really have to do that. And so instead of on exec instead of actually, we allocate the virtual address space, we'll allocate the address space, for the text and the data that sit in the file. But in the PTEs, we're going to just not map them at all. We're just going to keep, in the PTE for one of these pages, we're just going to not set the valid bit. So the valid bit is to 0. And of course, when we're going to get our first page fault. If we do this in exec, and let's say we modify x26 to do this, when will our first page fault happen? What's the first instruction that is being run for a user address or a user program? Where does a user program start?
Is it loading the initial code in UVM init?
Yeah, okay, we were just skip that piece, correct? That's the whole point of like modifying exec and not call to the UVM init where, so most, when we actually, if you remember from for regret or something like that, the place where an application starts is actually address 0. So like picture is a little bit, misleading here, but so here's text, here's 0, goes up to some number, and basically the first instruction, whatever sits here, that's the first instruction that we're going to actually, that address, that's the first instruction we're going to get a page fault on, right? Because we have not loaded it. Oops. So what to do on the page fault? Well, what we're going to do in the page fault is basically we'll note, this is was one of these on-demand pages. We have to remember somewhere earlier that this corresponds to some this corresponds to some file. And basically what we're going to do in the page fault handler is read that block or page from file into memory, map that memory into the page table, and restart the instruction. And then we're off and running, right? And so we're going to get, in the worst case, if the user program uses all of its text, uses all of its data, then we're going to get a page fault for every page, in the program. But if we get lucky and the program doesn't use all of its data segment or doesn't use all of its text segment, then we might save some memory, and we certainly make exec perform much quicker, and so it'll be a little bit more interactive. As soon as the program starts, boom, it's running. Well, and we hardly have to do any work in exec. Does that optimization make sense? Okay, so then there's a sort of a slight extension to demand paging. So this is the second part of demand paging. Yeah, sorry. Right, there's a more clearly. So part 2 of demand paging is the principle. There's a little bit of a problem here that we haven't really discussed. It might be the case, maybe the file that we're actually reading or the text and data segment are even bigger than what actually is in physical memory. Or if multiple applications started with demand paging, maybe there's some of their binaries is basically bigger than there actually is in physical memory. And so the typical thing, if you go down this demand paging route is to actually, if you run out of memory, so if calc returns 0, if out of memory, so for example, your demand page, you get a page fault at some page that needs to be paged in from the file system, but you don't have any more free pages, you need to do something. And so the typical, and this comes back to an earlier question, for example, the same is true for lazy or what to do if you run out of memory. So if you run out of memory, one option that you clearly have is to evict a page. You can, for example, instead of, you can, for example, evict the page and write it, to the file back. So, for example, if it's a data page that got modified, you can write it back, to the file system. And then once you evict the page, then you have a new free page, and you can put the use that, use the new, the just free page to satisfy, the fault that you had, and then basically restart the instruction again. And again, restart the instruction is a little bit more complicated because it's the whole machinery to basically do user read and start and transfer back to user space, etc. And so this is a typical operating system will do this. And of course, the key question is like, what page to evict? Which one to choose? So what are some candidates? What would be a reasonable policy for choosing a page to evict?
Least recently used.
Yeah, so this is the most commonly used strategy, least recently used. Or LRU. And that is the page that that's typically used, is thrown out. There's a couple sort of twists, typically so small optimizations that do. If you have to evict a page and you have a choice between a dirty page and a non-dirty page. So a dirty page is a page where there was a store to, and a non-dirty page is a page that basically only has been read, but not written to. Which one would you prefer to evict first?
A dirty one, because you would have to write the dirty one at some point anyway.
Yeah. So say again, actually, just make double check there.
I said dirty because 30 pages would need to be written to memory at some point.
Yeah, that's true. But then maybe now you have to write it twice. Once you write it, maybe it's modified later again. And so actually, typically, with an operating
Oh, I see. Okay.
with an operating system is exactly the opposite. They choose a page that actually has not been written or is not dirty because you don't have to do anything. You can just reuse it. You can just take, mark it, again, if it was present in page table 1, you mark it there as non-valid, and then you're done. And then you can reuse that page in another page table. So the preference in typically is to take pages that have been not, non-dirty ones first.
Can I just ask for a clarification on the dirty pages?
Yeah.
So I know, like in a cache, when we have memory and then we say, okay, a line is dirty because it hasn't been written to memory. But what about a page in memory? Like, what does it correspond to? Like, how is it dirty? Where does it have to be written back to? It just exists in memory, right? Isn't that the whole thing? Like, it doesn't exist anywhere else, really. So when can it be dirty?
Yeah, okay, so for example, if it is a demand page file page, actually we'll talk about this in a second, like in the next, maybe I prefetch a little bit too much, but if you, with memory map files, where you map a file into memory and then do store to it, then you would dirty that page.
Okay, so that only applies when like a page actually corresponds not just to some memory, but also to a file or something else.
Exactly.
Okay. Okay, that makes sense.
Yeah. Okay, so just to just to make two more points related to this. If you look at this, the PTEs again, so we saw this RSW bit, and you'll notice there actually is a bit 7, that is the dirty bit. So when the paging hardware, when the hardware ever writes, to a page, it will actually set the dirty bits. So the operating system later can see, this actually page, can easily see this page is actually written to. And similarly, there is an A bit that stands for access. And so whenever a page is either either read or written, the access bit will be set. And why is that useful to know? In what way could that help the kernel?
Well, the ones that haven't been accessed, you can evict, right?
Yeah, like, another way of saying that, if you want to implement least recently used, if you find a page that basically hasn't been accessed in some period of time, you know it actually hasn't been recently used. So it actually is a candidate for eviction, while the pages that have the access bit set are not really candidates for eviction. So the A bit is typically used, or the access bit is typically used to actually implement this LRU strategy.
Okay, but would you have to reset the accessed bits to not accessed every once in a while or something?
Yeah, exactly. That's exactly what the typical operating system will do. And if they don't do it maybe for all memory, they sweep through memory. So there's some famous algorithm for this called the clock algorithm. That is like one way of doing it.
Sorry, why would you need to set it? Why would you need to reset it?
Well, if you want to know whether a page is recently used, you make a periodic decision. Then say maybe every 100 milliseconds or whatever, every seconds, you clear the access bit. If it then gets accessed in the next 100 milliseconds, you know it was used in the last 100 milliseconds. And the pages that don't have the access bit set were not used in the last 100 milliseconds. And so then you can keep counters of like how intentionally they're used and what is and throw out the really, it's basically the stepping stone to be able to sort of sophisticate the LRU implementation. Okay, so I want to talk about one more, just to, and then that's the last one actually that you also will be implementing in one of the labs, and that is memory map files. And the idea is that here we have our address space. What we really want to do is basically be able to load a whole file or parts of the file into the address space, so that we can just manipulate the content of the file using load and store instructions instead of read, lseek and write. And to be able to support that, a typical operating system or most modern operating systems could provide a system call called nmap. And basically nmap takes a virtual address or picks a virtual address, length, protection, some flags, which I'm not going to talk about, and then a file descriptor of an open file and an offset. And basically what this says is like you should map this file descriptor. If this is address, the virtual address, the file descriptor starting from offset, in the file F, map that in at the address, at the virtual address VA, and do that with some protection like read, write, etc. And so let's say it's a read, write, then the kernel so the way the kernel implements nmap is if it does it eagerly, which is like most of the systems don't do it eagerly, it would basically copy, read all the bytes starting from offset, laying bytes starting from offset into memory, sets up the PTEs to point to the physical memory for where those blocks are located. And then basically from then on, the application can use load and store instructions to actually modify the file. And then maybe when where we're all done, there's typically a corresponding unmap call that unmap length that allows the application to say like, okay, I'm done with this particular file. And at the point of the unmap, we need to write back the dirty blocks. And we can easily figure out which blocks are dirty because they have the D bit set in the PTE. Now, of course, in any memory, sophisticated memory implementation, this is all done lazily. You just don't map the file immediately. You just keep a record somewhere on the site saying like, well, this PTE, really belongs to this particular file descriptor. So there's some information maintained on the site, which is typically called in the structure called the VMA or the virtual memory area. And for example, for this file F, that would be one VMA, and in that VMA we record, the file descriptor, the offset, etc. where the actual content of that memory should lives. And so when we get a page fault for a particular address that sits in this, VMA, then we can go off and the kernel can read it from disk and bring it into memory. And in response to an earlier question, this is like one of the reasons that this dirty bit is important, because at the unmap, you have to write back the dirty blocks. Does this make sense?
I have a quick question.
Yeah.
Maybe this is a more general issue, but could it ever be an issue if, say, multiple processes are memory mapping the same file on secondary storage, and then they like synchronization issues?
Yeah, good question. So what is the semantics in Unix in general? Like, what happens if multiple processes read and write to the same file using read and write system calls? Does Unix guarantee anything?
No, it's undefined.
Yeah, there's like no, the reads and write will show up in some order, or the writes will show up in some order. So if two processes write to the same block of a file, either the first process writes go or the second process writes go, one of the two. And so here's basically the same thing. We don't really have to guarantee anything. If you wanted to, a more sophisticated Unix operating system support file locking, where you can lock files and then you can properly synchronize. But by default, there's no synchronization. Or no synchronization at this level. That make sense?
I'm sorry, what is length and what is flags?
Oh, flags. Length is the length of the area you want to map the files, the number of bytes. Prod is read write X. Flags, is you'll see that when you do the unmap thing. This has to do with whether the area is mapped private or shared. If it's mapped shared, then it can be shared among multiple processes. Any further questions about this?
If some other process modifies the file on disk, that means that this will not be reflected here, right?
That's correct. Unless I think if it's mapped shared, then you're supposed to reflect those changes.
Right, but then they would be using the same file descriptor, right?
I'm hazy on the exact semantics of nmap when things are shared and what exactly happens there.
Okay, I guess in like the idiomatic case, yeah, in the shared, they would have to reflect it. But if a process just like actually opened the same file name completely separately, I think it could be unsynced even if it's shared.
Yeah, that's correct. Okay, so this after the file system lab, you actually do memory map files, and that will be our last virtual memory sort of lab, unless you decide at the end to do more virtual memory features or exercises, whatever you want to do. Anyway, so the main so to basically conclude this lecture, sort of the summary. We have looked in the past, sort of in great detail exactly, how page tables work. We've done a couple labs, one lab with page tables. We've looked a lot at like how traps work and page faults. And it turns out, if you combine the two, you can implement very powerful and elegant virtual memory features. And we went through a whole list of them, mostly focusing on the ones that are actually going to be implementing in future labs. But this is only a subset or a sample of the ones that some operating systems implement, and typical operating systems implement all the ones that actually discussed today. So you look at Linux, it has all of them, and many more interesting other tricks. But this hopefully gives you a good sense, sort of how the power of virtual memory. Once you dynamically can change the page tables in a page fault handler. And I think I'm exactly at 25, so maybe this is a good point to stop. But if you have any questions, feel free to ask them. And if not, I wish you good luck finishing the traps lab. And I hope it's not as painful as the or not as hard as the page table lab.
Sorry, I had another question. When you map in the previous slide, when you map the whole file, or like when you put it into memory, and it turns out to be longer than length, then what happens?
So if the file doesn't fit in the virtual address space,
Oh, I guess it was, so like length is how much of the file we want?
yes,
Or,
yeah. So length is just like we want to map like 10 bytes out of the file descriptor starting at offset off.
oh, okay, I see. So if the file is longer, then we're not gonna put all of it into memory.
Yeah, we can always, yeah, exactly.
Okay, I see. Thank you.
Thank you.
I've got a question. I've got a
See you
question
next week.
about evicting pages.
Yeah.
So, I guess, so we talked about it under like the man paging part 2, but is that like a general procedure we would use in any of these techniques if we discover that we're out of physical memory?
Yeah, as the common basically mechanisms. Like, so even in lazy allocation, we run at the point where there's no memory available anymore to allocate to a page. And, we support demand paging or whatever. We use evict, some page, typically using LRU.
Okay.
And one way to think about it is that in the steady state, the operating system basically runs with all memory in use at any time. And we want to use all memory. And so when we start something new, we have to make some room. And LRU is basically the way to do it.
Okay, makes sense. Thank you.